All right, let's talk about the Fibonacci sequence. You've probably heard of it, right? It's this super elegant pattern you see everywhere in nature. Think seashells, spiral galaxies, the whole shebang. It feels like one of those fundamental patterns that we've totally figured out. But what if it's been hiding something from us this whole time? So that's the big, fascinating question we're diving into today. What if, and this is a big what if, the world's most famous number sequence has a secret twin, a hidden sibling, just sitting there, overlooked for centuries? Yeah, let's really get into that idea. Okay, so first things first, let's do a super quick refresher on the classic Fibonacci sequence. You probably know the drill. It starts with 1 and 1. From there, you just add the two previous numbers to get the next one. So 1 plus 1 gives you 2, 1 plus 2 gives you 3, 2 plus 3 is 5, and it just keeps going like that, on and on. Simple enough, right? But if you look a little closer, something really interesting starts to pop out. There's this rhythm, this little pattern hiding in plain sight. It's all about whether the numbers are odd or even. You get an odd number, then another odd number, and then boom, an even one. And this little dance just repeats itself over and over without fail. Let's actually see it in action, because it's pretty cool. You've got 1 and 1, both odd, right? They're followed by 2, which is even. Then you get 3 and 5, both odd again, and they're followed by an even 8. You see it? This odd, even thing is totally consistent. And honestly, this simple little observation is the key that unlocks this whole new idea. Okay, and this is where the creative spark really hits. I mean, it's one thing to spot a pattern, but it's a whole other thing to ask, what if? The author of this idea looked at that odd, even structure and thought, hey, could that be more than just a coincidence? Could that be the actual blueprint, the rule for a whole new sequence that runs parallel to the original? And here it is. This is what came out of that big what if. On top, you've got our old friend, the classic Fibonacci sequence. And below it, this is the new proposed series. Now look closely. They start out exactly the same, 1, 1, 2. But right after that, they go their separate ways. The new one starts generating way more even numbers. So the big question is this just a random collection of numbers, or does it actually share the same mathematical DNA as the original? So how do we find out? We have to test it, right? We need to figure out if this even twin actually belongs in the Fibonacci family. And luckily for us, there's a classic, tried-and-true mathematical test for this. It involves a very special number, one that artists and mathematicians have been obsessed with for centuries. We're talking about the golden ratio test. See, one of the most amazing things about the Fibonacci sequence is this. If you take any number in the series and divide it by the one right before it, your answer gets closer and closer and closer to the golden ratio, also known as phi, which is roughly 1.618. So the logic is simple. If our new series is the real deal, it should pass this test. It should do the exact same thing. And, well, check this out. The numbers don't lie. This table shows the comparison. Just focus on that column on the far right for the new series. Yeah, it jumps around a little bit at the start, but look at what it's doing. Just like the classic one, it is zeroing in on that magical number, 1.618. This is like seriously powerful evidence. It really looks like we found a true sibling here. Okay, so the math is solid. It works. But, numbers can feel a little abstract. To really get a feel for a pattern like this, it helps to have a picture in your head. Like, what's the story here? What does this pattern actually look like in the real world? Well, for the classic Fibonacci sequence, the most famous story is all about rabbits. I'm sure you've heard this one. You start with one pair of rabbits. After a month, they're old enough to breed. After another month, they have a new pair. And if you track the number of pairs you have each month, what do you get? 1, 1, 2, 3, 5. It's a perfect match for the sequence. Okay, so if the original sequence is about multiplying rabbits, then what's the story for our new even series? To explain this one, the author came up with another really clever analogy, also from biology. Forget rabbits, think amoebas. In this model, we imagine amoebas that can be in two different states. We'll call them lowercase a and uppercase a. Think of lowercase a as an unfavorable condition, where the amoeba just survives but doesn't divide, and a is for a favorable condition where it splits in two. Following this new set of rules, this new branching logic, what numbers does it produce? 1, 1, 2, 4, 6, the new sequence. It's a totally different biological story, but it gets us to a remarkably similar mathematical place. So after spotting the initial pattern, building the new series from it, putting it to the test with the golden ratio, and even coming up with a whole new biological model for it, the author, A. Lukesh Kumar, came to this pretty confident conclusion. It's just a great example of how you build a solid case, right? One piece of evidence on top of another. But there's really one last step to making a mathematical discovery like this official. You've got to be able to describe it with a formula. Can you write a single rule, a recursion formula, that lets anyone, anywhere, generate this sequence without having to think through the whole amoeba thing every time? And this is it, the proposed formula to unlock the code. It's pretty straightforward, really. It basically says, look, your first three numbers are 1, 1, and 2. Just lock those in. After that, the rule is simple. To get any new number, just add the 2 that came right before it. This formula is like the official blueprint, the technical manual that lets anyone build this new sequence for themselves. When you step back and look at it, this whole thing has been a pretty amazing journey. It all started with just noticing a simple little pattern: odd, odd, even. And from there, it blossomed into a full-blown mathematical proposal. We got a new sequence, a proof that it works, a cool visual story to go with it, and even a formal formula. That's the process of discovery right there. And in the end, what's the biggest takeaway? This entire discovery happened because someone looked at something incredibly familiar and just saw it in a new light. It really makes you wonder, doesn't it? What kind of hidden patterns are all around you, just waiting for someone to notice? What simple, everyday thing could be the key to a brand new idea if you just decide to look at it with fresh eyes? Something to think about. Thanks for joining me on this one.